Hi there, Turgeon here, bringing you physics from afar. We got binoculars, we got our coats, we went outside, we smacked sticks together, and now we can figure out the speed of sound, at least at that temperature on that particular day. Here's some insights. When I say show all those steps, I mean use all this white space because you're going to want to do a couple of things. Number one, figure out exactly where everybody was standing. They weren't in the senior parking lot. They weren't on the baseball fields. Basketball court right here. Tennis court right here. Pond is right here. Here's the track, obviously. I know this seems like a different high school. It was our high school. And the bleachers are right here. And then what you can do is you can mark the two positions where we heard the simultaneous sound. Now I want you to think, see if you can figure it out. Which equation are we going to use? We know that there was a delay of 1 second between every strike of the two sticks. And we know that when we went far enough away, we heard absolutely no delay. From that, we can figure out how much time it took for the sound wave for each successive strike. And by the way, this is not a frequency. It's not like they were humming a tune. It's not like they were singing a particular tone or playing a certain repeating series of like repeating simple harmonic motion sounds. It wasn't like that, right? It was just there were individual strikes that were hitting our ear. If anything, the frequency that we're hearing is the very high frequency of the board itself being set into really short-lived oscillation, right? That thing was set into vibration of its own, has its own. I mean, just like this, each of these xylophones behind me, they each have their own. They each have their own tone that is dictated by how long they are, and also, of course, in that case, by the material they're made up of. Okay, so back to this. You want to figure out where you were located. Somewhere around here and somewhere around here. And then you can figure out the time it took. And the thing to remember is there's something about the speed of sound. If you look back at your notes, and it might have been in a video, there's an equation that we use for the speed of sound. Yes, there's V equals lambda F, but we don't know the wavelength and we don't know the frequency. This is another equation. Okay. And we're going to draw a sound wave, and there's two motions. And we're going to try to draw the sound wave with the particles. I mean, I guess you could draw this any way you want. I don't specifically say what does it really look like I did in the lab. Now, what is it actually that's oscillating in this diagram? And if you think about in a wave what it is that's actually moving, in the case of the sound wave, it's not going to be the sound wave. The sound wave is moving through space. Oops, I just gave you a little bit more than a hint for part B. Speed of sound faster in this situation. Look back at your notes. I'll give you a hint. It's not like you can't look at V equals lambda F and say, oh, if I look at V equals lambda F, I can increase the wavelength or increase the frequency. That won't work. I can't give you the answers to true, false. How about I say instead of true or false, I'll say that's not correct, or I'll say that's correct. Try your best. Talk to your neighbors, see if they agree, and then write your own true false question. This is in the notes. This is in the notes. This is in the notes actually about sound. If you picture how sound works, you can answer this, and you can answer this. We discussed in class. Some of these just involve a lot of these just involve thinking and application of the notes. Now, I'll tell you the equation that you're going to use here, if you haven't figured it out yet, is D equals VT. And then you're going to use this scale. Notice this, from here to here is 100 meters, and there are a bunch of rulers available. There's a spot in the classroom, which is where everything you need is. You go over to that same area, always the same area. Mr. Turgeon, where are the scissors? Mr. Turgeon, where are the rulers? Where's the scrap paper? Where's the tape and the stapler and the 3-hole punch? It's all in the same student area. We figured out the speed of sound. This has been Turgeon bringing you physics from afar.